Hello and welcome back. Mr. Johnson here, and in this video we're going to be looking at predicting products and specifically of decomposition and combustion reactions. Before we get started, again, I apologize if the audio sounds a little weird or if there's a glare on the board and you're not able to see some of the things that I'm writing, but unfortunately the technology that I typically use to make these videos isn't working right now, so making do with the best that I've got. But anyway, let's go on and move into this. So we're going to be looking at predicting products of decomposition and combustion reactions. Okay. In a previous video, I looked at predicting the products of synthesis reactions. And in that video, I talked about the fact that there are 5 types of chemical reactions. There's synthesis, decomposition, combustion, and then single and double replacement. I'm going to do another video on single and double replacement here shortly. But in this video, we're looking at decomposition and combustion reactions. And there's a couple of different types of decomposition reactions that we're going to look at. The first type that we are going to look at is this idea of metal carbonates decomposing into metal oxides and carbon dioxide. We're going to look at metal hydroxides, where you form a metal oxide and water. We're going to look at if we take a metal chlorate and what it forms, as well as the breakdown of an acid. But what we're going to see in each one of these examples is that for decomposition, we start with compound AB, and through decomposition or breaking apart, we get individual substances, typically 2 or more. So you'll see in the general reaction, AB yields A plus B. So compound AB decomposes into substance A and substance B. So again, those type of decomposition reactions that we can have metal carbonates, which is going to be a metal combined with CO2, okay, or CO3, sorry, carbonate, polyatomic ion, and in that decomposition form a metal oxide and CO2. You'll notice that this is the exact opposite of a synthesis reaction. Same thing if we take a metal hydroxide, so a metal and then the hydroxide polyatomic ion. If this decomposes, we're going to produce a metal oxide and water. Okay? So decomposition of metal carbonates and metal hydroxides, very similar in that in both of them we produce a metal oxide, but the second product is either going to be carbon dioxide or it's going to be water. Then we have metal chlorates. And when metal chlorates decompose, we end up getting the metal chloride and we produce water as that second product. Then the decomposition of an acid, where you're going to get a non-metal oxide and water, which again, if you go back and watch the synthesis video, we talk about how to synthesize an oxyacid using a non-metal oxide and water. So this is just the reverse process. And then we'll look at combustion in just a little bit. Okay? So let's go on and go through each of these types of decomposition reactions. So the first one, metal carbonates producing our metal oxide and carbon dioxide. I'm going to show you what I feel is the easiest way to go about predicting these products correctly. Okay? So first off, metal carbonate. So this is going to be something from column 1, column 2, or column 13 on your periodic table. Could also be a transition metal, which is perfectly fine. In the synthesis video, I didn't do any transition metals, but that is fully possible within those reactions for synthesis. I just didn't touch on them, okay? And I'm going to also not deal with transition metals for these. I think you'll get a basic understanding just using the examples that I'm going to give you. So let's start out with the fairly simple metal carbonate of sodium carbonate. So sodium carbonate would be Na2CO3, and then it decomposes. And the way that you can identify that you're dealing with a decomposition reaction is there's only ever going to be just one reactant. Okay? There's nothing for it to react with. The only thing that this can do is break apart. It can't exchange parts with anything else. It's not going to be able to combine with anything else because nothing else is there. These have to break apart. So that's what identifies as decomposition, that singular reactant. So when I see, in this case, that metal carbonate, within this carbonate, in essence, what we do is we subtract out CO2, and that's going to leave me with one oxygen. This CO2 that we subtract out, that's our first of the two products, because we're always going to produce a metal oxide and carbon dioxide. So I write it out as carbon dioxide first because I can easily kind of mentally subtract that CO2 from it. Then I'm going to take sodium. Again, we're going to look up charges, because anytime we form a compound, these compounds, especially in these cases, I'm dealing with a metal and a non-metal, which means they're going to be ionically bonded. And if they're ionically bonded, then I have to have a balance of charge. And the easiest way to do that is to look up the charge on the two components. Again, take that numerical value of the first charge and cross it down. Numerical value on the second charge, or second component, cross it down, and I get Na2O1. I cannot reduce those subscripts, so my formula for my metal oxide is Na2O. So I've taken my metal carbonate and I've produced my metal oxide and carbon dioxide, the two things I'm always going to produce when I break down a metal carbonate. So let's go and take a look at another example. Let's deal with, for example, magnesium carbonate, MgCO3. So again, when I notice that I've got a metal with carbonate, I'm going to subtract out CO2 as one of my products. When I subtract out that CO2, that leaves me with one oxygen remaining, which would have a 2 negative charge. My magnesium is going to combine with it. And again, we always combine things as ions. So magnesium as an ion would be a 2 positive. And like we've been doing, we cross down charges, initially get Mg2O2, but those subscripts can reduce, and I get a second product of magnesium oxide with the formula of MgO. So again, my metal carbonate produces the metal oxide and carbon dioxide. Let's do one more. Let's take aluminum carbonate. So now I would have Al2CO3 3. Okay? The reason being is carbonate has that -2 charge as a polyatomic ion. So this is where this 2 comes from. Aluminum is that 3 positive. That's where this 3 comes from. But it doesn't change up the products that I'm going to form. So again, the first thing I'm going to do is subtract out the CO2 as one of my products. And then that's going to leave me my oxygen, which is going to have a 2 negative charge. My aluminum, as I said just a moment ago, is a 3 positive. And we cross down those charges, and I get a formula for my metal oxide of Al2O3. So this is the decomposition of metal oxides, or metal carbonates, sorry. Metal carbonates always are going to produce a metal oxide and carbon dioxide. Okay, so second type of decomposition reaction that we can deal with, these are metal hydroxides. So let's start with just a basic one, NaOH, and no pun intended if you understand acid-base chemistry, because NaOH is a base. So starting out with the basic one, sorry. But when this decomposes, we're always going to end up producing a metal oxide and water. So when I look at this, when I see the OH group on there, that's my little trigger to remember that one of my products is going to be that of water, and my other product is going to be the combination of my metal and oxygen. So as a result, I'm going to take that sodium as Na, that oxygen as O, and like always, look up their charges. Sodium is a +1, oxygen is a 2 negative. Cross down those charges, which you're probably getting tired of hearing me say, but I'm going to continue saying it. And I get Na2O1, or simply Na2O. My metal oxide and water when a metal hydroxide decomposes. Let's take a look at another one. Look at MgOH2. Again, as soon as I say that there's only one reactant, I know this has to be decomposition. I then look at my components. I identify metal with hydroxide, and that hydroxide, I'm going to think about it in terms of, first and foremost, producing water. Then I'm going to take my metal and that oxygen and see what metal oxide forms. So Mg as a 2 positive, oxygen as a 2 negative. Cross down the charges. Mg2O2, but that reduces down to simply MgO. So again, I get my metal oxide and I get my water when a metal hydroxide decomposes. One more. Let's do aluminum hydroxide. Same process. So AlOH3. And when this decomposes, again, first and foremost, I produce water. Then I'm going to take my metal and that oxygen and combine those to get my metal oxide. So aluminum as a 3 positive, oxygen as a 2 negative. Cross down those charges, and we get Al2O3 as our metal oxide. So again, metal hydroxide decomposes always into a metal oxide and water. So that is the second type. And again, notice these are very similar to the decomposition of metal carbonates. The only difference is that when it's a hydroxide, you produce water along with that metal oxide. If this was a carbonate, I would produce CO2 along with the metal oxide. So very similar reactions. So the third type of decomposition. This again is the metal chlorates. Chlorate being the ClO4 polyatomic ion. And we produce a metal chloride and water. So let's take a look. Let's say NaClO4 decomposes. And when this decomposes, this is the easiest way that I know to think of this. Pardon me. Needed to cough real quick. All right. Sorry about that. I just realized chlorate is ClO3, not ClO4. My apologies. So continuing on. Again, apologies that I got the wrong polyatomic ion. I was thinking perchlorate. But this is sodium chlorate, ClO3. And when I produce products, I'm going to get the metal chloride, and then I'm also going to end up getting oxygen, okay, as that second component. So what I do, the way I see this, is I think about breaking that O3 off of there. I produce oxygen, and then I've got my metal, I've got my chlorine, and those are the two things that I'm going to end up combining to form my metal chloride. So again, cross over those charges, Na1Cl1, and I get NaCl as my product. Let's do another. Let's take magnesium chlorate. So MgClO3, 2, decomposes. So again, as soon as I see I've got metal with a chlorate, that oxygen, that's where I'm pulling and getting O2 from. Then I would have my metal and my chlorine. So magnesium as a 2 positive, chlorine as a 1 negative. And when I cross over those charges, Mg unwritten 1 Cl2, and I get MgCl2 as my metal chloride. So hopefully this is making sense, but let's look at one more. Let's go on and look at aluminum chlorate. So in this case, AlClO3, 3 decomposes. And when I see metal with the chlorate, I focus in on the oxygen. That oxygen is where I'm going to get my O2. Then I'm going to take my metal component, in this particular case aluminum, which should have a 3 positive charge, combine it with my chlorine as a 1 negative charge by crossing down, and I get AlCl3. Sorry, probably shouldn't write that as cursive. AlCl3, my aluminum chloride. So this is the decomposition of metal chlorides. Last type of decomposition that we're going to look at is the decomposition of acids. So in the decomposition of acids, we're always going to end up producing a non-metal oxide and then water. So take a look at, say, H2CO3. This is carbonic acid, which if you've watched the synthesis video, I explained how we would actually synthesize this. And what you'll see is that this is actually the exact reverse reaction. So in this, again, I'm going to produce a non-metal oxide and then water. So as a result, I'm going to take hydrogen and oxygen. That's going to produce my water. And then because I've, in essence, subtracted an oxygen from the CO3, that leaves me with the CO2. And that is my carbon dioxide, or my non-metal oxide, and then water. Okay. I could do this with other compounds as well, but as I explained in the synthesis video, the synthesis of oxy acids from a non-metal and water, it's kind of iffy. Same type of thing for the breakdown or the decomposition of acids, because while this is valid, okay, if you take and look at acid-base chemistry, we actually would not predict these two products. Okay? We would look at this acid as actually donating an H positive into solution. That's what makes the acid acidic. So this is, again, just like the synthesis of oxy acids, this is kind of a generalization. Okay? So when you see an acid, in other words, hydrogen combined with some other substance, you kind of have to take this with a grain of salt. Okay, but there it is in what you'll see in most textbooks, and I don't plan on doing a second example of this. Okay? Instead, I want to turn our attention to the last type of reaction for this video, and that is combustion. And when we talk about combustion, okay, this is where we're going to take and burn something in the presence of oxygen, and that is a key point to it. I can burn substances in the presence of hydrogen or nitrogen or argon or whatever, but we don't actually call it combustion unless it's burning in the presence of oxygen. And the most typical type of combustion reaction is you're taking a hydrocarbon, in other words, a substance or a compound that contains hydrogen and carbon as the majority elements. It can also contain oxygen in it. And you're reacting with oxygen. And the nice thing about combustion reactions is you always, 100% of the time, if you have complete combustion, in other words, all of your reactant is used up, you're always going to produce carbon dioxide and water. So, for example, if I take something like methane, CH4, and react this with oxygen, as soon as I recognize I've got a compound that is carbon and hydrogen, in other words, a hydrocarbon, and I'm reacting with oxygen, this is combustion, and I'm automatically going to produce CO2 and H2O, as well as heat energy or light energy. Same thing if I took something like C6H12O11, now reacted with oxygen. As soon as I see that the majority elements in this are carbon and hydrogen, making it a hydrocarbon, and it's reacting with oxygen, automatically I'm going to produce carbon dioxide and water. So that is combustion. Okay? Pretty straightforward and simple. I want to make note real quick, I didn't do this at the beginning of the video, but all the examples that I gave in this video, I didn't balance any of them. You would have to go back and balance the equations to make sure that you're observing the law of conservation of mass. Okay? So with that, if you have any questions, comments, or ideas for future videos, please let me know. I'd love to hear from you. If there's a topic that you can't find a good video on, you think I might be able to do it justice, please let me know. Okay? So as always, thanks for joining me, and take care.